Imagine a star so dense that a teaspoon of it would weigh billions of tons. That's a neutron star. But how do these cosmic remnants form and what makes them so extreme? Today, we'll uncover the science behind some of the strangest objects in the universe. If you enjoy this journey, please like, subscribe, share, and let us know your thoughts in the comments. Thank you for watching. Now let's begin. A neutron star begins its existence in the violent death of a massive star. Stars that are many times heavier than the Sun spend millions of years fusing lighter elements into heavier ones in their cores. At first, hydrogen fuses into helium, then helium into carbon and oxygen, and eventually heavier elements like silicon are fused until iron is produced. Iron cannot release energy through fusion. Once a core is filled with iron, fusion stops contributing outward pressure. The star has no further nuclear fuel to burn. Gravity, which has always been balanced by fusion pressure, suddenly dominates. The core begins to collapse inward. This collapse happens on a timescale of less than a second. The density of the core rises rapidly. Electrons are forced into protons, creating neutrons and neutrinos in a process known as electron capture. Neutrinos, which are extremely light particles, stream out in vast numbers. For a brief moment, nearly all of the gravitational energy of the collapse is carried away by these neutrinos. Astronomers estimate that about 99% of the energy released in a core collapse emerges as neutrinos. The remainder drives the violent explosion of the star's outer layers known as a core collapse supernova. The material that falls inward is compressed to nuclear densities. This means densities similar to those found inside atomic nuclei. The matter resists further compression because neutrons, like all fermions, obey the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state at once. Just as electron degeneracy pressure supports a white dwarf star, Neutron, degeneracy pressure along with repulsive nuclear forces halts the collapse before a black hole is formed. The result is a neutron star, a sphere only about 20 kilometers wide but with a mass that can be 1.5 times or even more than 2 times that of the Sun. The supernova that ejects the outer layers is among the most energetic events in the universe. It produces shock waves, bright optical light X-rays, and expanding clouds of gas. Observatories on Earth and in space can detect these remnants for tens of thousands of years after the explosion. The neutron star itself, left behind at the center, is hidden inside at first. As the remnant clears, it becomes visible to radio X-ray and sometimes even optical telescopes. Famous examples include the Crab pulsar born from a supernova witnessed on Earth in the year 1054. The physics of the collapse involves extreme forces that go beyond the conditions that laboratories on Earth can reproduce. The densities inside the forming neutron star exceed several 100 million tons per cubic centimeter. To give a sense of scale, a teaspoon of neutron star matter would weigh more than a mountain. These values are not guesses but are inferred from both theory and measurements of neutron star masses and radii. Observations of binary systems where neutron stars orbit companions allow astronomers to weigh them with high precision through orbital dynamics. Most measured neutron stars are between about 1.2 and 2 times the mass of the Sun. Their compactness, implied by general relativity and observations of surface temperatures, matches the predictions of nuclear density matter. In some cases, the collapse may happen through a slightly different pathway called an electron capture supernova. This occurs in stars that are not quite massive enough for full iron core formation. Instead, their cores are composed of oxygen, neon, and magnesium. When electron capture starts in these elements, the pressure drops suddenly, and the core collapses. The end result is still a neutron star, but the explosion is less energetic than that of a massive iron core collapse. These events are thought to contribute to the population of relatively low-mass neutron stars, Evidence for them comes from supernova observations that appear fainter, and from population modelling of stellar evolution. The initial conditions of the collapse shape many of the neutron star's later properties. The rotation rate of the progenitor star is preserved and amplified as the core contracts. Just as a spinning skater turns faster when pulling in their arms, the collapsing star spins more quickly as its radius shrinks from thousands of kilometers to only about 20 kilometers. This conservation of angular momentum means that many neutron stars are born rotating dozens of times per second. Magnetic fields are also carried inward and strengthened by the collapse. This leads to surface fields trillions of times stronger than Earth's magnetic field. These initial spins and fields are crucial for later observable phenomena such as pulsars and magnetars. The collapse also releases neutrinos in vast numbers. In fact, the direct detection of neutrinos from a nearby supernova in 1987, known as supernova 1987A, confirmed this picture. Detectors in Japan and the United States recorded about 24 neutrinos arriving within seconds of each other just before the light from the supernova reached Earth. This was a small number compared to the total flux, but it matched the predictions for core collapse. The detection demonstrated that the formation of a neutron star indeed floods the universe with neutrinos. The aftermath of collapse is not entirely uniform. Some stars may collapse further into black holes if the mass of the core exceeds the limit that neutron degeneracy pressure can withstand. This limit, known as the Tolman-Oppenheimer-Volkoff limit, is estimated to be around 2 to 3 times the mass of the Sun, though its exact value depends on the uncertain physics of dense matter. Observations of neutron stars with masses up to about 2.3 times the mass of the Sun suggest that matter remains stable, at least to those densities. Beyond that, collapse into a black hole seems inevitable. Thus, neutron stars occupy a narrow range of masses bridging the gap between white dwarfs and black holes. The formation of a neutron star represents a transition from ordinary matter to one of the most extreme states known. The atoms that once made up the star are stripped apart, leaving neutrons packed together at densities comparable to atomic nuclei. The outer crust is rich in nuclei and electrons, but the core is essentially a sea of neutrons. This fundamental change in matter is one reason neutron stars are so important to physics. They provide natural laboratories for conditions unreachable on Earth. The process of birth also seeds the cosmos with heavy elements. During the supernova shock heating and rapid neutron capture nucleosynthesis occur forming elements heavier than iron. These are expelled into interstellar space. Thus, the death of a massive star both creates a neutron star and enriches the galaxy with the raw material for planets and life. Observational evidence from supernova remnants shows spectral lines of heavy elements such as nickel and cobalt confirming these nuclear processes. From collapse to explosion to compact remnant, the story of how a neutron star is born is a story of balance lost and a new equilibrium found. Gravity overwhelms nuclear fusion, matter is crushed to nuclear densities, neutrinos carry away the energy, and a star's life ends with a new object that will persist for millions or even billions of years. The neutron star born in an instant becomes one of the universe's most enduring and enigmatic objects. A neutron star is an object that combines extreme mass with extremely small size. Its diameter is only about 20 kilometers, yet its weight exceeds that of the Sun. This compactness defines its nature and creates physical conditions that are not found elsewhere in the universe apart from black holes. To understand its density, it is helpful to compare with familiar examples. The Earth has an average density of about 5 grams per cubic centimeter. A white dwarf star, which is already compact, reaches about 1,000,000 grams per cubic centimeter. A neutron star goes far beyond this level, with central densities measured in hundreds of millions of tons per cubic centimetre. These values are inferred from careful observation and theoretical models rather than from direct sampling, but the agreement between different methods gives strong confidence in their accuracy. The weight of neutron stars is constrained through binary systems. When a neutron star has a companion, its orbit can be tracked through timing measurements of pulses or changes in the companion's light. From these orbital motions, astronomers determine masses with high precision. Most known neutron stars fall between about 1.2 and 2.2 times the mass of the Sun. Some individual measurements indicate objects heavier than 2.3 solar masses, pushing close to the theoretical limit that matter can withstand without collapsing further into a black hole. The radius is measured by analyzing X-ray emissions from the surface. When a neutron star accretes matter, bursts of X-rays are produced. The detailed spectrum and timing of these bursts allow researchers to estimate surface area. Another method is to study how light is bent by the gravitational field of the neutron star, an effect predicted by general relativity. Light paths curve as they escape, and with careful modelling this reveals the true radius. Most measurements converge on radii of about 11 to 14 kilometers. Together, the observed mass and radius provide valuable constraints on the equation of state, the relationship between pressure and density in ultra-dense matter. The compactness also sets extreme conditions at the surface. Gravity there is about 100 billion times stronger than on Earth. The escape speed required for a particle or photon to leave is close to half the speed of light. This immense gravity means that the neutron star strongly bends light, making it appear larger, and distorting the way surface features are seen from a distance. These effects have been confirmed by observations of X-ray hotspots that shift in ways consistent with light bending. Newly formed neutron stars are very hot with surface temperatures of millions of degrees. They radiate strongly in X-rays, but over time they cool. Cooling occurs first through neutrino emission from the dense core and later through electromagnetic radiation from the surface. Young neutron stars can be seen by their soft thermal X-rays, while older ones fade and are detected mainly through radio or high-energy emissions tied to their magnetic fields. Cooling curves plotted from multiple observations of neutron stars of different ages provide indirect evidence for processes inside such as neutron superfluidity. The mass range that allows a neutron star to exist is narrow. If the collapsing core has too little mass, the remnant is a white dwarf supported by electron degeneracy pressure. If the mass exceeds a critical value, collapse does not halt at neutron degeneracy, but continues into a black hole. The upper mass limit, called the Tolman-Oppenheimer-Volkoff limit, is thought to lie somewhere between 2 and 3 times the mass of the Sun. Its exact value depends on the uncertain physics of matter at high density. Discoveries of neutron stars above 2 solar masses demonstrate that matter remains stable to at least that threshold. Inside, the structure changes with depth. The crust contains nuclei arranged in a solid lattice and supported by a sea of electrons. At greater density, neutrons begin to leak from nuclei, producing a region known as the neutron drip layer. Further inward, the composition becomes a dense fluid of mostly neutrons, with small numbers of protons and electrons. Deeper still, at the very center, matter may take exotic forms not yet confirmed, possibly involving hyperons or free quarks. Even the outer crust, though, is denser than anything that can be replicated in laboratories. Rotation is also affected by compactness. As the progenitor star collapses, angular momentum is conserved, causing the neutron star to spin very quickly. Many are born rotating dozens of times each second, and in some cases through later interactions with a companion star they can be spun up to hundreds of rotations per second. This stability against breaking apart during such rapid rotation is only possible because of the immense density. The small size of neutron stars makes them difficult to observe directly in visible light. Most appear only through their pulses of radio waves, their bursts of X-rays, or their gravitational influence on companions. In rare cases, very young neutron stars can be observed optically as faint points, such as the Crab pulsar located in the center of its expanding remnant. In most cases, however, specialized instruments are needed to detect their signatures. The compactness also affects the energy released when matter falls onto the star. In binary systems, accreting matter spirals inward and forms a disk before striking the surface. The gravitational potential energy released in this process is enormous. Per unit mass, it is far greater than the energy produced by nuclear fusion in ordinary stars. This is why neutron star binaries are among the brightest X-ray sources in the sky. When two neutron stars orbit each other, their compactness ensures strong gravitational interactions. Over millions of years, they lose energy by emitting gravitational waves causing their orbit to decay. Eventually, they merge in a process detected by gravitational wave observatories. The signal encodes information about their masses and radii, providing further checks on theoretical models. The match between observed signals and predictions confirms the extreme compactness inferred for neutron stars. Neutron stars, therefore, are defined by scale. Their small size combined with heavy mass creates the high density, strong gravity, and energetic processes that make them unique. Measurements of their mass and radius achieved through careful observations of binaries and emissions anchor the study of dense matter. These values are not only numerical descriptors, but also the physical basis for understanding all the extraordinary behaviors that arise from such compact objects. The structure of a neutron star is layered with each region marked by changes in composition and density. Starting from the outside, the surface appears as a thin crust, only about 1 kilometer thick, yet this layer alone contains material with properties that are far beyond what is found on Earth. The outer crust is made of nuclei and electrons arranged in a crystalline lattice. These nuclei are mostly iron and heavier elements that were left behind during the supernova explosion. Electrons move freely in this lattice and provide pressure support. Even though the density of this outer crust is already immense, it is still low compared with deeper regions. Beneath the outer crust lies the inner crust. As density increases, atomic nuclei are packed so tightly that neutrons begin to leak out of them. This process is called neutron drip. Free neutrons coexist with nuclei and electrons, forming a dense mixture. In this regime, the pressure from degenerate neutrons becomes increasingly important. The inner crust extends several hundred meters deep and transitions gradually into the core. The matter here is already beyond laboratory conditions, and its behavior is studied through nuclear theory and constrained by astronomical observations. Deeper still is the outer core region where free neutrons dominate. The matter here is mainly neutrons with smaller fractions of protons, electrons, and possibly muons. This mixture is extremely dense, several times higher than nuclear density, and supports the bulk of the neutron star against gravity. Neutrons at these densities are expected to behave as a quantum fluid with properties of superfluidity that change how heat and momentum are transported. The outer core is where many of the observable features of neutron stars, such as cooling and rotational stability, are determined. The innermost region, called the inner core, remains uncertain. It may contain neutrons and protons arranged in unusual ways, or it might include exotic states of matter that are not normally stable. Theories suggest possibilities such as hyperons, which are particles containing strange quarks, or even deconfined quark matter, in which quarks are no longer bound into neutrons and protons but move freely. These scenarios are difficult to test directly, but measurements of the maximum neutron star mass and radius put constraints on what the core can contain. If quark matter or other exotic particles exist, there they must still provide sufficient pressure to support the star against collapse. The boundaries between these regions are not sharp in the way that layers of the Earth are. Instead, transitions are gradual, with matter changing its arrangement as density increases. For example, in the crust, as nuclei are squeezed together, they change shape from spheres to rods and sheets before dissolving into uniform nuclear matter. These transitional structures are known as nuclear pasta, and will be described more fully in another context, but they represent the complex physics of matter under extreme compression. Understanding the structure of neutron stars is important because it determines their thermal evolution, their rotational behavior, and their response to external forces. The crust, for example, can fracture under stress, leading to sudden changes in rotation known as glitches. The core, by contrast, behaves more like a fluid and supports superfluid currents that couple to the crust over long timescales. Observations of glitches in pulsar timing provide evidence for these layered behaviors. The outer crust also controls how a neutron star interacts with its surroundings. Magnetic field lines are anchored in the crust, so stresses in the solid lattice can distort or shift the field. When these stresses are released suddenly, they can produce bursts of radiation observed in magnetars. The thermal conductivity of the crust also determines how heat flows from the core to the surface, influencing how quickly a young neutron star cools. Space telescopes that measure surface temperatures give indirect evidence of these internal processes. The transition from the crust to the core marks the point where matter is no longer organized into nuclei but becomes uniform nuclear matter. This transition occurs at densities close to that of atomic nuclei. In laboratories on Earth, nuclear collisions can probe similar densities for very short times, providing some guidance, but only neutron stars maintain such conditions stably. Thus, neutron stars serve as natural laboratories, preserving states of matter that are otherwise unreachable. The outer core is also the region where many of the star's properties are set. The balance between neutrons and protons determines how neutrinos are produced, which in turn affects cooling. The strength of superfluidity in the neutrons and superconductivity in the protons changes how heat and magnetic fields evolve. Different theoretical models predict different cooling curves, and observations of young neutron stars provide checks on these models. For example, the neutron star in the Cassiopeia, a supernova remnant, shows rapid cooling that is interpreted as evidence for superfluid neutrons in the core. The inner core remains the most mysterious. At densities several times that of atomic nuclei, new interactions become possible. Theoretical physics suggests that hyperons, which include strange quarks, could appear. Alternatively, a phase of quark matter may be present where quarks are no longer confined within protons and neutrons. If this happens, the pressure-density relationship changes, influencing the maximum possible neutron star mass. Observations of very heavy neutron stars place limits on how soft the equation of state can be, ruling out some models of exotic cores. Future measurements of gravitational waves from neutron star mergers may provide further evidence, since the way neutron stars deform during in spiral depends sensitively on their inner structure. The layered structure of a neutron star also explains why they can survive for billions of years without collapsing. Each layer provides a balance of forces from the electron lattice in the crust to the neutron degeneracy pressure in the core. Gravity is immense, but at every level, quantum mechanical principles provide resistance to compression. The crust resists through electron degeneracy and lattice forces, while the core resists through neutron degeneracy and nuclear interactions. This balance produces a stable object that can persist long after the explosion of its progenitor star. Measurements of neutron star structure are not direct, but come from multiple sources of evidence. Timing observations of pulsars, thermal measurements of cooling surfaces, X-ray spectra from accreting binaries and gravitational wave signals from mergers all contribute pieces of the puzzle. Together they confirm that neutron stars are not uniform spheres, but complex layered objects whose interiors hold matter in states otherwise unknown. Inside, a neutron star matter takes on states that are unlike anything encountered in ordinary conditions. At the high densities found in the core, neutrons and protons are packed so tightly that their behavior is governed by quantum mechanical rules on a macroscopic scale. One of the most important consequences is that neutrons are expected to form a superfluid. A superfluid is a state of matter that flows without viscosity. In a neutron star core, this means that neutrons can move without resistance, transporting heat and angular momentum in ways that differ greatly from normal fluids. Evidence for neutron superfluidity comes from observations of neutron star cooling and from sudden changes in rotation called glitches. Cooling data show that some neutron stars lose heat faster than expected, which can be explained by neutrino emission processes enhanced by the pairing of neutrons into superfluid states. Pulsar glitches, which are abrupt jumps in rotation frequency, are also consistent with the presence of a superfluid interior that stores and releases angular momentum. Protons, which are much fewer in number than neutrons, are also expected to pair up under these conditions. In the dense interior, protons form a superconducting fluid. Superconductivity refers to the complete absence of electrical resistance, and in a neutron star core it means that magnetic fields are carried by quantized flux tubes rather than diffused evenly. The interaction of these magnetic flux tubes with the vortices of the neutron superfluid is thought to play a role in the rotational dynamics of the star. The coupling between superconducting protons and superfluid neutrons influences how the crust and the core exchange angular momentum, providing a possible explanation for long-term timing behaviors seen in pulsars. The existence of superfluidity and superconductivity is supported indirectly through multiple observations. One of the strongest pieces of evidence comes from the young neutron star in the Cassiopeia, a supernova remnant. Over a period of about a decade, astronomers observed that its surface temperature dropped significantly faster than predicted by standard cooling models. This rapid cooling can be explained if neutrons in the core undergo a transition to a superfluid state, releasing energy in the form of neutrinos. The timing of the observed temperature decline matches the theoretical expectation for such a phase transition. This connection provides one of the most compelling confirmations that quantum fluids exist inside neutron stars. Theoretical models predict that superfluidity in neutron stars occurs because neutrons, like electrons in superconductors, can form Cooper pairs. These pairs arise when two fermions, which individually cannot occupy the same quantum state, interact through an attractive potential that allows them to bind together as a composite boson. Bosons do not obey the same exclusion principle and can condense into the same state, giving rise to collective quantum behaviors such as superfluidity. In neutron stars, the pairing is driven by nuclear forces at very high densities. The details of the pairing mechanism and the temperature at which the transition occurs depend on the equation of state, which remains an open area of research. Superfluidity alters how angular momentum is stored and redistributed. In a rotating superfluid, angular momentum is carried by quantized vortices, tiny cylindrical regions where the fluid circulates. In the neutron star interior, billions of such vortices are arranged in a lattice that maintains the overall spin. When the crust slows down due to magnetic braking, these vortices can become pinned to the lattice of the crust. Stress builds up as the superfluid interior continues rotating more quickly than the crust. Eventually, vortices unpin in large numbers, transferring angular momentum suddenly to the crust and producing a glitch. This physical picture connects the microscopic properties of neutron superfluidity to macroscopic astronomical observations. Superconductivity in protons has equally important consequences. Magnetic fields inside the star are not smoothly distributed, but confined to quantized tubes called fluxoids. The arrangement and movement of these fluxoids determine how magnetic fields evolve. Over long timescales, the interaction between fluxoids and neutron vortices may lead to changes in both rotation and magnetism. For example, the gradual decay of magnetic fields in old neutron stars may be influenced by the slow movement of these quantized structures through the star. This interplay remains an active area of theoretical research because it connects the interior state of matter to observable surface phenomena. Another exotic feature predicted at these densities is the presence of muons. Muons are heavier cousins of electrons, and at high densities the Fermi energy of electrons becomes large enough that muons appear to balance charge. Their presence alters the composition and contributes to the pressure balance. In some models, other particles such as hyperons, which contain strange quarks, may also form in the core. If this happens, the equation of state softens, making the star more compressible. However, because neutron stars are observed with masses above 2 solar masses, the equation of state cannot be too soft. This provides constraints on how much exotic matter can exist inside. The overall picture is that the interior of a neutron star is not a static solid, but a dynamic quantum system. Superfluid neutrons allow heat to move rapidly and alter how the star cools. Superconducting protons control the behavior of magnetic fields. Additional particles, if present, change the pressure balance. Observational signatures such as cooling rates, glitches, and magnetic field decay all point toward the existence of these unusual states. Though not directly visible, they leave imprints on measurable properties that telescopes can detect. Understanding these states of matter also helps connect astrophysics with nuclear physics. Experiments on Earth using heavy ion collisions attempt to recreate dense conditions for brief moments, providing data on nuclear interactions. These results are combined with astrophysical observations to refine models of dense matter. Neutron stars thus serve as natural laboratories for superfluidity and superconductivity under extreme conditions, complementing experimental work. The combination of theory, laboratory data, and astronomical measurement creates a consistent picture in which exotic quantum states dominate the interior of these compact stars. In practical terms, the conformation of superfluidity and superconductivity in neutron stars shows that quantum mechanics governs behavior on macroscopic scales. Instead of being confined to atoms or laboratory materials, these states extend across objects larger than entire cities. Every rotation, every cooling curve, and every magnetic field change in a neutron star carries the imprint of these collective quantum phenomena. The calm, steady pulsations seen from Earth are the outward sign of matter organized in the most unusual ways allowed by physics. As density increases deeper inside a neutron star, matter passes through transitions that lead to structures known as nuclear pasta. This name reflects the shapes that nuclear matter takes on under extreme compression. In the crust at densities lower than that of atomic nuclei, matter is arranged as spherical nuclei embedded in a sea of electrons and free neutrons. As density rises, the spacing between nuclei decreases until the repulsive and attractive nuclear forces cause them to deform. Instead of remaining spherical, they elongate into rods that resemble spaghetti. At still higher densities, the rods merge into sheet-like structures similar to lasagna. Beyond that, voids form within uniform matter, producing shapes sometimes compared to tubes or bubbles. Together, these unusual arrangements are referred to as nuclear pasta phases. These structures are predicted by nuclear physics calculations and simulations that model how nucleons interact under compression. The basic idea is that at intermediate densities between those of normal nuclei and uniform nuclear matter, the system minimizes its energy by forming non-spherical geometries. The balance of forces that determines these shapes includes the short-range attraction between nucleons, the repulsion at very short distances, and the long-range Coulomb repulsion of protons. The result is an array of complex repeating patterns that extend throughout regions of the inner crust. Although nuclear pasta cannot be studied directly in a laboratory, its properties influence observable phenomena. One key effect is on the thermal conductivity of the crust. The irregular shapes scatter electrons more effectively than a uniform lattice would, reducing heat transport. This means that the cooling behavior of neutron stars depends partly on how much nuclear pasta is present and how it is arranged. Another effect is on neutrino emission. Nuclear pasta may provide channels for enhanced neutrino scattering, altering how the star loses energy. Observations of neutron star cooling curves are used to test these possibilities. The mechanical properties of nuclear pasta are also important. The structures are predicted to be extremely strong, perhaps stronger than any material known. Simulations suggest that the elastic properties of these phases could support mountains only centimeters high on the surface of the star, yet even such tiny irregularities are significant. Because neutron stars rotate rapidly, any asymmetry in their shape can generate gravitational waves. Nuclear pasta, by supporting slight deformations, may allow neutron stars to radiate gravitational waves continuously as they spin. Searches with gravitational wave observatories aim to detect such signals, though none have yet been confirmed. Another implication of nuclear pasta concerns pulsar glitches. The crust of a neutron star is solid while the interior is superfluid. Stress between the two layers can build up as the star spins down due to magnetic braking. When the crust fractures, angular momentum is suddenly transferred, producing a glitch. The strength of the crust and the presence of nuclear pasta affect how much stress can be stored and how it is released. This connection makes nuclear pasta an important part of understanding timing irregularities observed in pulsars. The study of nuclear pasta also links astrophysics to nuclear experiments on Earth. Heavy ion collisions can produce matter at similar densities for very brief times, and the scattering patterns from such experiments can be compared with simulations of pasta phases. While not identical to the conditions in neutron stars, these experiments provide valuable constraints on nuclear interaction models. The agreement between terrestrial experiments and astrophysical observations strengthens confidence in the existence of pasta-like phases inside neutron stars. From a theoretical perspective, nuclear pasta illustrates how matter self-organizes under extreme conditions. The transition from nuclei to rods to sheets, and then to uniform matter, is a sequence of phases governed by energy minimization. Each structure represents a balance between surface energy, which favors compact shapes, and Coulomb energy, which favors spreading out protons. The resulting compromise is geometries that repeat in space, but differ from anything familiar in ordinary matter. Such structures are not just exotic curiosities, but play real roles in how neutron stars behave and evolve. Astronomers cannot see nuclear pasta directly, but its fingerprints appear in several types of data. Cooling rates of young neutron stars provide evidence for modified heat transport. Glitches and timing irregularities point to strong crustal structures capable of storing stress. The absence of continuous gravitational wave detections places limits on the maximum deformations supported by the crust, which in turn constrains pasta properties. Each of these pieces adds to the picture of a layered neutron star interior shaped by unusual nuclear matter. The existence of nuclear pasta highlights the fact that neutron stars are not uniform objects, but are structured at multiple scales. At the atomic level, nuclei deform into rods and sheets. At the macroscopic level, these arrangements influence global phenomena like heat flow, magnetic field stability, and spin evolution. By connecting microscopic physics to astronomical observations, the study of nuclear pasta shows how neutron stars bridge scales from quantum interactions to stellar dynamics. In the calm, steady pulses received from distant neutron stars, there is hidden complexity. The signals that seem so regular are shaped in part by the strange geometries of matter deep within. Though hidden from direct view, the rods, sheets, and bubbles of nuclear pasta influence how these stars shine, how they cool, and how they tremble. Neutron stars thus remind us that even in the most extreme environments, matter organizes itself in intricate ways dictated by the laws of physics. The intense magnetic fields of neutron stars originate during the collapse of their progenitor stars. A normal massive star possesses a magnetic field generated by motions in its convective interior, similar in principle to the dynamo that operates in the Sun. When the core of the star collapses, magnetic flux is conserved. This process, called flux freezing, means that as the size of the core decreases, the strength of its magnetic field increases dramatically. If a star with a radius of hundreds of thousands of kilometers collapses into an object only about 20 kilometers wide, the surface magnetic field is amplified by many orders of magnitude. Even if the progenitor star had a field comparable to the Sun's modest field, the resulting neutron star could reach field strengths of 1 trillion times stronger than Earth's magnetic field. These magnetic fields are not uniform across all neutron stars. Typical pulsars, which are observed as regular radio beacons, usually have fields in the range of about 100 million to 1 trillion times the strength of Earth's field. Some neutron stars, however, possess even stronger fields exceeding 1 quadrillion times Earth's field. These extreme cases are called magnetars and represent a distinct class of neutron stars with unique observational properties. The initial conditions of the collapsing star, including its rotation and magnetic field configuration, likely determine whether the remnant emerges as a pulsar, a magnetar, or a more quiescent neutron star. The field is anchored in the crust and threaded through the superconducting core, where it is confined to quantized magnetic flux tubes. The arrangement of these tubes influences how the field evolves over time. Because protons in the core behave as a type of superconductor, magnetic fields do not diffuse freely, but are locked into narrow structures that interact with the neutron superfluid vortices. This interaction couples magnetic evolution to rotational dynamics, creating a deep link between magnetism and spin behavior. Over time, magnetic fields decay, though the rate depends on the properties of the star. Ohmic dissipation, Hall drift, and ambipolar diffusion are the main processes that govern field decay. Ohmic dissipation occurs as currents in the crust encounter resistance, slowly converting magnetic energy into heat. Hall drift involves nonlinear interactions among field components rearranging field lines without immediately reducing their energy. Ambipolar diffusion occurs in the core, where charged particles move relative to neutrons under magnetic stresses. The relative importance of these processes depends on temperature composition and the strength of the field itself. Observationally, magnetic field decay is inferred from pulsar timing. A pulsar's spin rate slows down as rotational energy is lost through electromagnetic radiation, a process known as magnetic braking. By measuring the rate of spin down and assuming it is caused primarily by magnetic dipole radiation, astronomers can estimate the strength of the magnetic field. These estimates reveal a wide range of field strengths and provide evidence that fields weaken over millions of years. Younger neutron stars have stronger fields, while older pulsars show weaker fields consistent with slow decay. Magnetars provide dramatic examples of magnetic energy release. Their fields are so strong that they can stress the crust until it fractures. When the crust shifts suddenly, magnetic reconnection occurs, releasing bursts of X-rays and gamma rays. Observations of giant flares from magnetars show energies that exceed those of ordinary pulsar emissions by many orders of magnitude. The largest recorded magnetar flare, detected in 2004 from a source in our galaxy, released in a fraction of a second as much energy as the Sun emits in hundreds of thousands of years. These events are rare, but illustrate the potential of magnetic fields to dominate the energy output of neutron stars. The connection between magnetic fields and emission is also seen in ordinary pulsars. The rotation of a neutron star with a tilted magnetic axis causes beams of radio emission to sweep across space. The detailed shape and stability of these beams depend on the structure of the magnetosphere, which is controlled by the magnetic field. Changes in field configuration can alter pulse shapes and timing stability. Long-term monitoring of pulsars provides a way to study how magnetospheres evolve and how magnetic energy is dissipated. The strength of a neutron star's field also influences how it interacts with a companion star. In binary systems where matter is transferred from a companion, the magnetic field can channel the accreting plasma onto the magnetic poles, creating hotspots that radiate X-rays. The balance between the field strength and the inflow of matter determines whether accretion reaches the surface or is halted at the magnetosphere. This balance produces a range of phenomena from X-ray pulsars to systems where accretion is disrupted entirely. Magnetic fields play a role in neutron star evolution across timescales. Immediately after birth, rapid rotation and strong magnetic fields drive powerful winds that can strip surrounding material and shape the expanding supernova remnant. Over thousands to millions of years, fields control spin down, determining how long a pulsar remains active as a radio source. Over tens of millions of years, field decay alters the observational appearance, eventually leaving behind stars that are too weakly magnetized to shine as pulsars. Through each stage, magnetism remains central to the life of the star. The study of neutron star magnetism provides a testing ground for plasma physics and electrodynamics under extreme conditions. The magnetospheres of neutron stars are filled with electron-positron pairs accelerated to relativistic speeds, emitting radiation across the spectrum. These environments cannot be reproduced in terrestrial laboratories, but their behavior can be modeled through simulations and checked against observations. Each radio pulse, each magnetar flare, and each X-ray hotspot provides evidence for the extraordinary influence of magnetic fields in shaping what we see. Neutron star magnetic fields are among the strongest in nature, second only to those of black holes accreting at high rates. They determine how energy is emitted, how spin evolves, and how matter is channeled. The diversity of neutron star behavior, from the steady ticking of radio pulsars to the violent bursts of magnetars, can largely be traced back to differences in magnetic field strength and configuration. By observing these stars across the spectrum and over decades of monitoring, astronomers piece together how fields are born, how they evolve, and how they eventually fade. Among neutron stars, a small but remarkable group are known as magnetars. These objects possess magnetic fields that are far stronger than those of ordinary pulsars. Estimates place their surface fields at more than 1,000,000,000 times stronger than Earth's field levels, so extreme that even the structure of atoms would be distorted. The presence of such fields means that magnetic energy dominates the behavior of the star, instead of being powered primarily by rotation. As in normal pulsars, magnetars are powered by the decay and rearrangement of their magnetic fields. This distinction explains why magnetars are observed mainly through bursts of high-energy radiation rather than steady radio pulses. The first evidence for magnetars came from observations of soft gamma repeaters and anomalous X-ray pulsars. Soft gamma repeaters are sources that emit repeated bursts of gamma rays and X-rays. These bursts are not as energetic as those from classical gamma ray bursts, but occur more frequently and from localized sources within the galaxy. Anomalous X-ray pulsars, by contrast, emit persistent X-rays without showing the expected signs of accretion from a companion star. The unifying explanation for both phenomena is the existence of a neutron star with an exceptionally strong magnetic field. The energy released in bursts and steady emission comes from the twisting reconnection and decay of magnetic field lines inside and around the star. The crust of a magnetar plays a key role in these events. The magnetic field is anchored in the solid crust, and as the field evolves, it exerts stress on the lattice of nuclei. When the stress becomes too great, the crust fractures. These starquakes shift magnetic field lines, suddenly producing reconnection events that accelerate particles and release bursts of X-rays and gamma rays. The raise time of these bursts, often measured in milliseconds, indicates how quickly the crust can crack and magnetic energy can be liberated. The short duration but high intensity of the bursts reflects this rapid release of stored energy. In some rare cases, magnetars produce giant flares that dwarf normal bursts in energy output. These events release in a fraction of a second as much energy as the Sun emits in hundreds of thousands of years. The most powerful flare observed came from a magnetar in the constellation Sagittarius in 2004. The initial flash was so intense that it briefly affected Earth's ionosphere despite the source being tens of thousands of light-years away. After the initial spike, the flare often shows a decaying tail of radiation, modulated by the rotation of the magnetar, revealing the hotspots on its surface created by the event. Such giant flares demonstrate the extreme capacity of magnetic fields to store and release energy. Not all magnetar activity is explosive. Many magnetars show steady X-ray emission that gradually decays over years. This emission is thought to be powered by the slow decay of magnetic fields which heat the crust and surface. The persistence of this emission, even when rotation is relatively slow, confirms that magnetic decay rather than rotational energy is the main power source. By tracking the long-term luminosity of magnetars, astronomers learn about the timescales over which fields decay and about the thermal conductivity of the crust. The presence of strong fields also affects the magnetosphere. In magnetars, the magnetic pressure is so high that the region around the star is filled with dense plasma. Twisting of field lines can drive currents that emit X-rays and gamma rays. Resonant scattering of photons by magnetospheric particles modifies the observed spectra, producing characteristic features that distinguish magnetars from other neutron stars. Modeling these spectra allows researchers to infer the configuration and strength of the magnetic field near the surface. Magnetars are relatively rare. Only a few dozen have been confirmed in our galaxy compared with thousands of ordinary pulsars. This rarity suggests that only certain progenitor stars produce the conditions necessary for magnetar formation, likely involving rapid initial rotation and high magnetic flux. Despite their small numbers, magnetars play a disproportionately large role in astrophysics because of their energetic outbursts and their potential link to other high-energy phenomena such as fast radio bursts. Some models propose that at least a fraction of the mysterious millisecond duration radio flashes observed from extragalactic sources could be produced by magnetar activity, though this remains an open question. The life cycle of a magnetar involves gradual decline of its magnetic field. Over tens of thousands of years, the field decays to the point where bursts become less frequent, and the star resembles an ordinary neutron star. This timescale is consistent with the observation that most known magnetars are relatively young, associated with supernova remnants only a few thousand years old. As they age, their activity wanes and they become difficult to distinguish from other neutron stars unless their thermal emission remains unusually high. The study of magnetars continues to advance as new observatories detect more events across the spectrum. X-ray telescopes reveal bursts in steady emission, while gamma-ray detectors record giant flares. Radio telescopes have recently discovered that some magnetars can emit pulsed radio waves, though with properties distinct from ordinary pulsars. The combination of multi-wavelength observations builds a comprehensive picture of how magnetic energy dominates these extraordinary objects. Magnetars illustrate the extreme limits of magnetic physics. Their fields are so strong that they reshape atomic structure, crack solid crusts and power bursts that can affect Earth from across the galaxy. They show that magnetic energy, when concentrated in such an environment, becomes one of the most powerful forces shaping astrophysical phenomena. In the quiet but intense X-ray light of a magnetar, one can trace the invisible lines of magnetic tension that bind the star and govern its violent release of energy. Rotation is one of the most defining properties of neutron stars. When the core of a massive star collapses, its angular momentum is conserved. The radius shrinks by a factor of tens of thousands, and the spin rate increases by the same proportion. As a result, newly formed neutron stars can rotate many times per second. Some spin even faster with periods of just a few milliseconds. This rapid rotation has profound effects, powering beams of radiation and shaping the magnetosphere. The most famous consequence of rotation is the pulsar phenomenon, in which a neutron star appears as a regularly flashing beacon across the sky. The concept of a pulsar arises from the geometry of rotation combined with magnetism. A neutron star's magnetic axis is usually not aligned with its spin axis. Radiation produced by charged particles moving along magnetic field lines emerges in narrow beams near the magnetic poles. As the star rotates, these beams sweep across space like the light from a lighthouse. If Earth lies in the path of the beam, observers detect a pulse of radio waves or high-energy photons each time the beam passes. The repetition rate of the pulses corresponds to the spin period of the neutron star, making pulsars some of the most accurate cosmic clocks known. The discovery of pulsars in the late 1960s provided direct evidence for the existence of neutron stars. The first pulsar, known as CP1919+21, emitted radio pulses every 1.3 seconds with remarkable regularity. At first, the regularity was so surprising that the discoverers considered whether it might be an artificial signal. Soon, however, additional sources were found confirming a natural origin. Since then, thousands of pulsars have been catalogued, each with its own spin rate, pulse shape, and spectrum. These objects remain a primary tool for studying neutron star rotation and magnetism. The spin rates of pulsars cover a wide range. Some rotate once every few seconds, while others rotate hundreds of times per second. Millisecond pulsars, which spin at hundreds of rotations per second, are often found in binary systems where accretion from a companion has transferred angular momentum to the neutron star. This process, known as recycling, spins up an old slow pulsar into a rapid rotator. Millisecond pulsars are extremely stable in their timing, rivaling atomic clocks in precision. This stability makes them valuable tools for detecting gravitational waves through pulsar timing arrays. By monitoring small changes in pulse arrival times from many millisecond pulsars, astronomers hope to detect the influence of passing gravitational waves stretching and compressing space. Radiation from pulsars is not limited to the radio band. Some pulsars emit X-rays and gamma rays powered by the acceleration of particles in their magnetospheres. Observations with space telescopes such as the Fermi Gamma Ray Space Telescope have revealed pulsars shining brightly at high energies. The combination of radio and gamma ray data provides a more complete picture of how pulsar beams are generated. The precise mechanisms remain under study, but they involve electric fields induced by rotation, which accelerate particles to near light speed. These particles emit curvature radiation and synchrotron radiation, producing the observed beams. The regularity of pulsar timing is both a scientific tool and a probe of their internal physics. Most pulsars slow down gradually over time as rotational energy is lost to electromagnetic radiation and particle winds. The rate of spin down can be measured with extraordinary precision. By comparing the spin period and its derivative, astronomers infer the magnetic field strength and age of the pulsar. Young pulsars tend to spin faster and slow down more quickly, while older pulsars spin slowly and show little change. This progression outlines the life cycle of pulsars from energetic young objects to fading remnants. Occasionally pulsars show sudden irregularities. These include glitches in which the spin rate jumps forward abruptly and timing noise in which small unpredictable variations appear. Glitches are thought to arise from interactions between the superfluid interior and the solid crust, while timing noise may reflect instabilities in the magnetosphere. Both phenomena demonstrate that pulsar timing, though usually stable, carries imprints of complex processes inside and around the neutron star. The beam geometry of pulsars also varies widely. Some beams are narrow, producing sharp pulses, while others are broad with complex multiple components. The shape of the beam depends on the arrangement of magnetic field lines and the location of emission regions in the magnetosphere. By studying pulse profiles across many pulsars, astronomers map the variety of magnetic configurations and emission mechanisms. These studies reveal that while the lighthouse model explains the general behavior, the details involve intricate plasma physics that is still not fully resolved. In addition to isolated pulsars, there are binary pulsars in which a neutron star orbits another star. The motion of the pulsar in its orbit causes variations in pulse arrival times that can be modeled to reveal orbital parameters with high accuracy. Binary pulsars have been essential for testing general relativity. The first binary pulsar, discovered PSR 1913+16, showed orbital decay consistent with energy loss by gravitational radiation. This provided the first indirect evidence for gravitational waves decades before direct detection. Pulsar timing continues to serve as a probe of both fundamental physics and stellar astrophysics. Rotation also connects neutron stars to their surrounding environments. Young pulsars often create pulsar wind nebulae in which relativistic particles flow outward, producing synchrotron radiation visible in X-rays and radio waves. The Crab Nebula is a well-known example, powered by a pulsar rotating 30 times per second. The energy lost from the spin of the pulsar maintains the nebula's brightness long after the supernova explosion. These systems demonstrate how rotational energy is transformed into electromagnetic radiation and particle acceleration. The study of neutron star rotation and pulsars has become one of the most detailed branches of astrophysics. By observing pulse timing profiles and spectra, astronomers gain information about magnetic field strength, interior physics, binary dynamics, and even the structure of spacetime itself. Each pulse arriving with clock-like precision across cosmic distances carries the imprint of a dense star spinning in darkness. Rotation is thus not only a defining feature of neutron stars but also a bridge between their hidden interiors and the signals detectable from Earth. Although pulsars rotate with remarkable stability, many of them exhibit sudden irregularities in their spin known as glitches. A glitch is an abrupt increase in the rotation rate of a neutron star, usually followed by a gradual relaxation back toward the expected trend. These events provide important clues about the internal dynamics of neutron stars, particularly the interaction between the superfluid interior and the solid crust. The first glitches were detected in young pulsars such as the Vela pulsar, which rotates about 11 times per second, and has shown numerous glitches since its discovery. Each glitch involves a fractional change in rotation of only a few parts per million, but because pulsar timing is so precise, these small shifts are clearly measurable. The leading explanation for glitches involves the presence of superfluid neutrons in the inner crust and outer core. In a rotating superfluid, angular momentum is carried by quantized vortices. These vortices can pin themselves to the lattice of nuclei in the crust. As the crust spins down due to magnetic braking, the superfluid continues to rotate faster because its vortices are held in place. Over time, a differential rotation builds up between the crust and the interior superfluid. Eventually, the pinning force can no longer hold the vortices, and they unpin, suddenly moving outward and transferring angular momentum to the crust. This causes the star's surface to spin up abruptly, producing the observed glitch. After the event, frictional forces gradually couple the superfluid and crust again, leading to the slow relaxation seen in post-glitch timing. Glitches vary in size and frequency depending on the pulsar. The Vela pulsar experiences large glitches roughly every few years, while the Crab pulsar shows smaller, more frequent ones. Some pulsars show only a handful of glitches over decades of monitoring, and others display none at all. This diversity suggests that the internal structure and temperature of each star influence the glitch mechanism. Younger pulsars with higher internal temperatures may have weaker pinning forces, and thus more frequent but smaller glitches. Older pulsars may have stronger crustal structures, leading to larger but rarer events. In addition to glitches, pulsars often exhibit timing noise, a term used for irregular variations in spin that do not follow a predictable pattern. Timing noise may reflect instabilities in the magnetosphere or small-scale movements of superfluid vortices. While glitches are discrete, easily recognized events, timing noise appears as a wandering of the pulse period when measured over months or years. Both phenomena show that neutron stars, though often thought of as perfect cosmic clocks, are influenced by complex processes within their interiors and magnetospheres. Another possible cause of glitches is crustal fracture. As the star spins down, its shape becomes more spherical. The solid crust must adjust to this change and stress can build up. When the stress exceeds the braking strain, the crust cracks, altering the moment of inertia of the star and producing a sudden spin-up. This starquake model may work in combination with the vortex unpinning model, with the crustal fracture triggering the release of pinned vortices. Nuclear pasta structures in the inner crust may provide additional strength that allows large stresses to accumulate, making glitches more dramatic. The study of glitches provides unique information about superfluid physics. On Earth, superfluid helium shows similar behaviors with quantized vortices, but neutron star conditions are vastly more extreme. The presence of glitches demonstrates that superfluidity operates across scales of kilometers inside stars, influencing their rotation on observable timescales. By analyzing the size and frequency of glitches, astronomers can estimate the fraction of the star's moment of inertia that is contained in the superfluid. This fraction provides constraints on the thickness of the crust and the coupling between layers. Some pulsars also display so-called anti-glitches, sudden decreases in rotation rate. These are rarer than ordinary glitches and may involve different mechanisms possibly linked to magnetospheric events, rather than internal superfluid dynamics. For example, sudden reconfigurations of magnetic fields in magnetars could cause changes in torque that appear as anti-glitches. Observations of such events broaden the range of phenomena connected to neutron star rotation. Glitches have further implications for astrophysics beyond the study of superfluidity. The sudden release of energy associated with unpinning events or crustal fractures may produce observable emission. Some glitches are accompanied by changes in pulse shape or increases in X-ray brightness, suggesting that energy is deposited into the magnetosphere. These connections help link internal dynamics to external signals. In the case of magnetars, glitches are sometimes coincident with bursts of gamma rays, reinforcing the idea that crustal and magnetic stresses are intertwined. Monitoring glitches also helps refine pulsar timing models. For pulsar timing arrays that aim to detect gravitational waves, understanding and correcting for glitches is essential. A sudden spin change can mimic or obscure the subtle timing shifts caused by passing gravitational waves. Long-term monitoring of many pulsars helps distinguish between internal rotational irregularities and external influences on pulse arrival times. Thus, glitches while complicating pulsar timing also provide valuable astrophysical insight. The statistics of glitches across the pulsar population reveal trends that help shape theory. Large frequent glitches are mainly seen in young energetic pulsars, while millisecond pulsars rarely glitch. This pattern fits with the idea that superfluid coupling and crustal strength evolve with age. As neutron stars cool and their interiors change, the nature of angular momentum transfer shifts. Each glitch, therefore, is not just a rotational hiccup but a probe into the hidden physics of dense matter. Through decades of observations, glitches have transformed from curiosities into essential tools for studying neutron star interiors. They show that beneath the steady ticking of pulsars lies a dynamic interplay of superfluid vortices, crustal stresses and magnetic forces. Each sudden spin-up is a reminder that even the most stable cosmic clocks are governed by the complex physics of matter, compressed beyond nuclear density. In addition to solitary neutron stars, many exist in binary systems where they orbit a companion. These systems provide some of the clearest insights into how neutron stars interact with their environment. Companions can range from ordinary stars to white dwarfs and even other neutron stars. The presence of a companion alters the observable behavior of the neutron star, since gravitational interaction, mass transfer and orbital dynamics all leave measurable signatures. Binary systems also allow astronomers to weigh neutron stars with high precision, since the orbital motion can be tracked and modelled. When a neutron star is in a close binary with a normal star, it can accrete material from its companion. As the companion evolves and expands, gas flows from its outer layers toward the neutron star. Because of angular momentum, the infalling gas forms a disk rather than falling directly onto the surface. This accretion disk heats up as gravitational energy is converted into thermal energy, emitting brightly in X-rays. Such systems are called X-ray binaries, and many of the brightest X-ray sources in the sky are neutron stars accreting from companions. The strong gravity of the neutron star means that even a small amount of accreted matter produces a large release of energy. The behavior of the accretion depends strongly on the magnetic field of the neutron star. If the magnetic field is relatively weak, material can reach the surface through the disk, spreading across the star and heating it uniformly. If the field is strong, it channels the flow onto the magnetic poles, creating localized hotspots. As the star rotates, these hotspots come into and out of view, producing X-ray pulsations. Such X-ray pulsars provide direct evidence of the connection between magnetic field geometry and accretion. By analyzing the pulse profiles, astronomers can deduce the alignment of magnetic and spin axes, as well as details of the accretion flow. In some systems, accretion is intermittent. Transient X-ray binaries spend most of their time in a quiescent state, then brighten dramatically when accretion resumes. These outbursts are caused by instabilities in the accretion disk, which build up matter and then release it suddenly. Monitoring these outbursts provides a view into how matter behaves under the influence of extreme gravity and magnetic fields. The timescales of these events, ranging from weeks to months, reflect the physics of disk viscosity and thermal balance. Another outcome of binary interaction is the recycling of pulsars. When an old neutron star accretes matter from a companion over long periods, the angular momentum transferred spins it up to much higher rates. This process creates millisecond pulsars which rotate hundreds of times per second and emit highly stable radio pulses. The companion in such systems is often a white dwarf left behind after it has donated much of its material. Millisecond pulsars are therefore considered old neutron stars rejuvenated by binary evolution. Their timing stability makes them valuable as cosmic clocks for fundamental physics experiments, including the detection of gravitational waves from distant supermassive black hole binaries. In tighter systems, neutron stars and their companions exchange mass in more dramatic ways. Some binaries contain two neutron stars orbiting each other. These double neutron star systems are rare but crucial for testing theories of gravity. Their orbital dynamics can be measured precisely through pulsar timing, allowing tests of general relativity. The Hulse-Taylor binary pulsar discovered in the 1970s provided the first indirect evidence for gravitational waves by showing that its orbit was shrinking at exactly the rate predicted by gravitational radiation. More recently, direct detections of merging neutron stars by gravitational wave observatories confirmed these predictions and revealed additional details about binary evolution. Binary interactions can also strip companions of most of their mass. In so-called black widow systems, a millisecond pulsar bombards its companion with radiation, and particle winds gradually evaporating it. These companions can be reduced to extremely low masses, sometimes only a fraction of the mass of Jupiter. Observations of such systems show the powerful influence of pulsar winds and demonstrate that neutron stars can profoundly reshape their stellar neighborhoods. The orbital properties of binary systems provide further insights. Some neutron stars are in wide, stable orbits where accretion is minimal, while others are in very close orbits with orbital periods of only a few hours. In close binaries, tidal forces and gravitational radiation play major roles in the evolution of the orbit. Over time, orbital decay can lead to mergers producing powerful gravitational wave signals and kilonova explosions. These mergers are a key source of heavy elements such as gold and platinum, linking binary neutron star evolution directly to cosmic nucleosynthesis. Accreting neutron stars also show bursts of nuclear burning on their surfaces. When hydrogen and helium accumulate from a companion, they can ignite in runaway thermonuclear reactions producing X-ray bursts. These bursts last for seconds to minutes and are observed as sudden spikes in X-ray brightness. They provide information about the composition of the accreted material and the conditions on the neutron star surface. Some systems exhibit superbursts, which last for hours, and are thought to be caused by the ignition of carbon at greater depths. These phenomena reveal how nuclear physics operates under extreme gravity and pressure. Binary systems highlight the versatility of neutron stars. Depending on orbital separation, mass transfer rates, and magnetic field strength, they can appear as steady X-ray pulsars, transient bursters, recycled millisecond pulsars, or sources of gravitational waves. Each case provides unique observational windows into the physics of dense matter magnetic fields and strong gravity. The diversity of outcomes shows how a neutron star's environment shapes its evolution and observable properties. Through detailed study of binaries, astronomers connect theory with measurement. Pulsar timing, X-ray spectroscopy, orbital dynamics, and gravitational wave detection all converge to build a consistent picture of how neutron stars behave when partnered with other stars. These systems demonstrate that neutron stars are not isolated relics, but active participants in binary evolution, exchanging mass, angular momentum, and energy with companions in ways that illuminate some of the most extreme processes in astrophysics. When matter from a companion star falls onto a neutron star, the conditions at the surface allow for some of the most energetic thermonuclear reactions in the universe. Gas pulled from the companion forms an accretion disk, and then flows onto the neutron star's surface where it is compressed by intense gravity. As hydrogen and helium accumulate in a thin layer only a few meters deep, temperature and pressure rise until nuclear fusion ignites explosively. This process produces what astronomers call Type 1 X-ray bursts. These bursts are sudden, bright flashes of X-rays that rise quickly in intensity and then decay over tens of seconds to minutes. They were first detected in the 1970s by space telescopes and have since been studied in detail by modern missions. The physics of these bursts is well understood. The layer of accreted matter behaves like fuel spread across the neutron star's surface. As more material piles up, density and temperature increase, until fusion reactions of hydrogen into helium and later helium into heavier elements ignite uncontrollably. Unlike the steady fusion that powers ordinary stars, these reactions occur in runaway fashion, because the thin layer cannot expand enough to regulate temperature. The result is a thermonuclear explosion that releases an enormous amount of energy in a very short time. The entire neutron star surface can be engulfed, producing luminosities close to the Eddington limit, the maximum brightness a star can sustain before radiation pressure drives material away. Observations of X-ray bursts provide information about the neutron star surface and the nuclear reactions involved. The rise and decay times of bursts reveal how heat is transported through the accreted layer and into the crust. Spectra measured during bursts show changes in temperature that can be modelled to estimate the star's radius and mass. In some bursts, photospheric radius expansion occurs. This happens when radiation pressure lifts the outer atmosphere above the surface before it settles back down. Measuring this effect allows astronomers to place constraints on the Eddington luminosity, and thus on the neutron star's properties. In addition to ordinary bursts, there are superbursts that last for several hours. These are thought to be triggered by the ignition of carbon deep in the accreted layer, after many normal bursts have built up heavier ashes. The energy released in superbursts is 1,000 times greater than in ordinary bursts. Their rarity and long duration make them more difficult to study, but they provide insight into nuclear processes at greater depth and higher density. The existence of superbursts confirms that neutron star surfaces are sites of repeated nuclear burning cycles, building up complex chemical compositions over time. Accreting neutron stars also show variability linked to magnetic fields. In systems where the field is strong, accreted matter is funneled onto the magnetic poles, creating localized hotspots. These hotspots rotate with the star producing pulsations in the X-ray light curve. Such X-ray pulsars allow astronomers to study the geometry of the accretion flow and the alignment of magnetic and spin axes. The periodicity of pulses also provides an accurate measure of the neutron star's rotation rate and how it evolves under the influence of accretion. In some systems, accretion spins up the star significantly, eventually producing millisecond pulsars. Another phenomenon observed in accreting systems is quasi-periodic oscillations, variations in X-ray brightness, that occur at frequencies linked to the orbital motion of matter in the inner accretion disk. These oscillations are thought to arise from inhomogeneities in the disk or from interactions between the disk and the star's magnetic field. The highest frequency oscillations approach kilohertz values corresponding to matter, orbiting only a few kilometers above the neutron star surface. Studying these signals provides information about strong gravity, since the orbital frequencies depend on the curvature of spacetime near the star. Accretion onto neutron stars is also efficient at converting gravitational energy into radiation. The energy released per unit mass of accreted material is about 10 to 20% of the rest mass energy, far higher than nuclear fusion in ordinary stars. This is why X-ray binaries containing neutron stars are among the brightest sources in the X-ray sky. Their luminosities can vary from persistent emission at high levels to transient outbursts when accretion becomes unstable. These changes are monitored by space telescopes that survey the X-ray sky, continuously providing a record of how matter behaves under extreme gravity. Some accreting neutron stars show bursts that are not purely thermonuclear, but instead related to instabilities in the accretion flow. In these cases, sudden increases in mass transfer from the companion trigger episodes of enhanced emission. The interplay between thermonuclear bursts and accretion-driven variability makes these systems complex laboratories for both nuclear physics and accretion physics. Understanding the relative contributions requires long-term monitoring and detailed spectral analysis. Accreting neutron stars are also important for studying the long-term evolution of neutron star crusts. As material accumulates and undergoes nuclear burning, heavier elements are produced and buried deeper into the crust. This process alters the composition and thermal properties of the crust. When accretion halts in transient systems, the crust cools, and its thermal relaxation can be observed in X-rays. Such cooling curves provide direct evidence of heat transport and conductivity in the crust, revealing properties of dense matter under extreme pressure. The combination of accretion and nuclear burning also plays a role in recycling pulsars. As mass and angular momentum are transferred, the neutron star spins up and its magnetic field may decay. Eventually, the system can settle into a stable millisecond pulsar with a faint white dwarf companion. These recycled pulsars are among the most stable rotators in the universe, yet their history is written in the bursts and accretion episodes that shaped them. Through X-ray bursts, pulsations, quasi-periodic oscillations, and thermal relaxation, accreting neutron stars reveal the interplay of gravity magnetism and nuclear reactions. Each burst is a momentary signal of nuclear fire ignited under conditions no laboratory can reproduce. Each pulse is a trace of material guided by immense magnetic fields. Together they provide a detailed picture of how neutron stars interact with companions and how matter behaves when pushed to the limits of density and pressure. Neutron stars are not only remarkable for their density and magnetic fields, but also for the way their gravity bends space and time. They provide some of the best laboratories for testing general relativity in the strong field regime, where the effects of space-time curvature are far more intense than in our solar system. Light that leaves the surface of a neutron star is bent, significantly altering the way the star appears to observers. This bending means that more than half of the surface is visible at once, since photons emitted from the far side can be curved around to reach the observer. The degree of light bending depends on the compactness of the star, the ratio of its mass to its radius. Careful modelling of this effect allows astronomers to constrain neutron star sizes and to test predictions of general relativity under extreme gravity. Another effect measurable with neutron stars is the Shapiro delay. This phenomenon occurs when pulses from a pulsar pass near the gravitational field of a companion star. The strong gravity of the companion slows the passage of the radio waves, adding a delay that depends on the mass and geometry of the system. By measuring these tiny changes in pulse arrival times, astronomers can determine the masses of both stars with high precision. The Shapiro delay has been used to weigh several neutron stars, accurately providing critical data on the maximum masses they can sustain before collapsing into black holes. These measurements also confirm the predictions of general relativity about how gravity affects the travel time of light. Frame dragging is another relativistic effect observable near neutron stars. A rotating massive object twists the surrounding space-time, an effect predicted by Einstein's theory, and called the lens-Thirring effect. In binary systems with rapidly spinning neutron stars, frame dragging can influence the orbital motion of companions or the orientation of accretion disks. While difficult to measure directly, hints of this effect are found in quasi-periodic oscillations in X-ray binaries, where orbital frequencies near the neutron star surface show patterns consistent with frame dragging. Future observations with more sensitive timing instruments may allow direct tests of this effect in neutron star systems. Gravitational redshift is also important. Photons climbing out of the deep gravitational well of a neutron star lose energy, causing their wavelengths to shift to longer values. This redshift means that spectral lines from the surface appear at different energies than they would under normal conditions. Measuring this effect requires high-resolution spectroscopy, and while it is challenging due to the faintness of neutron star surfaces, some candidate detections have been reported. If confirmed, gravitational redshift measurements would provide direct evidence of the compactness and test predictions of relativity. Binary pulsars have been especially powerful tools for studying relativity. The orbital motion of pulsars and their companions is tracked with extreme precision through pulse timing. These systems show several relativistic effects, including periastron advanced gravitational time dilation and orbital decay due to gravitational radiation. The Hulse-Taylor binary pulsar was the first case where orbital decay was measured and found to match general relativity's prediction of energy loss by gravitational waves. This discovery earned a Nobel Prize and provided indirect confirmation of gravitational waves decades before they were directly detected by observatories. Since then, other binary pulsars have confirmed these predictions to even higher accuracy, establishing neutron star systems as essential laboratories for gravity. One of the most precise systems studied is the double pulsar PSR J0737 3α39, where both members of the binary are visible as pulsars. This system allows multiple independent tests of general relativity. Observed phenomena include Shapiro delay, gravitational redshift, periastron advance, and orbital decay. All measurements match the predictions of general relativity to within a fraction of a percent. Such precision is unmatched in any other astrophysical context, and demonstrates that neutron stars probe gravity, where it is strongest, but still outside the event horizon of a black hole. The role of neutron stars in testing relativity extends beyond binary timing. Their strong gravity influences accretion flows, producing observable effects in X-ray spectra and timing. As matter spirals inward, orbital frequencies reflect the curvature of spacetime. Models of kilohertz. Quasi-periodic oscillations include relativistic corrections such as the innermost stable circular orbit, a prediction of general relativity that sets a limit on how close stable orbits can exist. Observing these oscillations allows indirect probing of spacetime geometry near the neutron star. Although uncertainties remain, these studies complement timing tests by exploring relativity in dynamic accretion environments. The study of extreme gravity around neutron stars also links to gravitational wave astronomy. When two neutron stars orbit each other closely, their inspiral produces gravitational waves that encode information about the masses, radii, and tidal deformability of the stars. The tidal effects are particularly important because they depend on how compressible the neutron star material is, which ties directly to the equation of state of dense matter. The detection of GW117, a binary neutron star merger, provided the first direct evidence of such effects. Analysis of the gravitational wave signal placed limits on neutron star radii and confirmed that general relativity holds even in the violent merger of compact objects. Neutron stars thus serve as natural experiments for general relativity, bridging the gap between weak field tests in the solar system and the inaccessible interiors of black holes. They allow measurements of time dilation, light bending, redshift, orbital decay, and frame dragging in conditions where spacetime curvature is extreme but observable. Each precise pulse, each spectral shift and each gravitational wave event adds another confirmation that the fabric of space-time behaves as Einstein's theory predicts. At the same time, these tests push the limits of knowledge, since any deviation from general relativity might reveal new physics. Through their rotation, their magnetism, and above all their gravity, neutron stars provide windows into fundamental laws. Observations from radio telescopes, X-ray observatories and gravitational wave detectors converge to show that relativity remains accurate in the strong field regime. Yet because neutron stars are not black holes, their interiors are still made of matter, allowing the additional opportunity to study how dense matter and curved space-time interact. This unique combination makes neutron stars some of the most valuable objects in the universe for exploring the relationship between matter and gravity. When two neutron stars orbit one another, their mutual gravity gradually causes the orbit to shrink as energy is carried away by gravitational waves. Over millions or even billions of years, this spiral brings the stars closer until they eventually merge. The final stages of this process are among the most dramatic events in the universe. As the stars spiral together, the frequency and amplitude of the emitted gravitational waves increase, creating a signal often described as a chirp. Observatories such as LIGO and Virgo detect these signals, allowing astronomers to measure the masses and radii of the merging neutron stars. The detection of G70817 in 2017 marked the first time such a merger had been directly observed, and it confirmed many predictions of general relativity and astrophysics. During the spiral tidal forces deform the neutron stars, slightly changing the gravitational wave signal. The amount of deformation depends on how compressible the star is, which in turn depends on the equation of state of dense matter. By analysing the waveform carefully, scientists can place limits on neutron star radii and internal structure. This makes mergers a valuable probe of nuclear physics as well as gravity. The precise measurement of tidal deformability in G7, 7, 8, and 7 indicated that neutron stars are relatively stiff with radii in the range of about 11 to 14 kilometers. Such constraints rule out some theoretical models that predict overly soft equations of state. When the two stars finally collide, the result can vary depending on their combined mass. In some cases, the merged object collapses immediately into a black hole. In others, it forms a hypermassive neutron star that survives for milliseconds to seconds before collapsing. In either case, the collision ejects material at high velocity. This ejected matter undergoes rapid neutron capture nucleosynthesis, also known as the R process. In this process, nuclei rapidly absorb neutrons and then undergo beta decay, building up heavy elements such as gold, platinum, and uranium. The kilonova associated with G70817 was observed in visible and infrared light and showed spectral signatures of newly formed heavy elements. This confirmed that neutron star mergers are a major source of the universe's heaviest elements. The electromagnetic counterpart of a merger is called a kilonova, because it is about 1,000 times brighter than a typical nova. Kilonovae are powered by the radioactive decay of R-process nuclei in the ejected matter. Their light curves evolve over days to weeks, starting blue and becoming redder as heavier elements dominate the opacity. Observing kilonovae provides direct evidence of nucleosynthesis and connects gravitational wave signals to chemical enrichment in galaxies. The detection of both gravitational waves and light from GW170817 mark the dawn of multi-messenger astronomy, in which different kinds of signals are combined to provide a full picture of astrophysical events. Neutron star mergers also produce bursts of high-energy radiation. In GW170817, a short gamma-ray burst was detected about 2 seconds after the gravitational wave signal. This confirmed that at least some short gamma-ray bursts are produced by neutron star mergers. The mechanism involves the formation of a relativistic jet powered by the accretion of material onto a black hole or hypermassive neutron star. When the jet is oriented toward Earth, a brief flash of gamma rays is observed. Even when the jet is off-axis, afterglows at X-ray optical and radio wavelengths can be detected as the jet interacts with surrounding material. The multi-wavelength afterglow of GW170 or 817 provided unprecedented data on the physics of relativistic jets and the structure of the surrounding environment. The study of mergers is not limited to individual events. By detecting more mergers, astronomers can measure the rate at which they occur in the universe. This rate informs models of binary stellar evolution, showing how often massive stars form in pairs and survive successive supernovae to become double neutron star systems. It also constrains the contribution of mergers to the cosmic abundance of heavy elements. If neutron star mergers are frequent enough, they may account for most of the gold and platinum in the universe. If they are rarer, other sites such as rare classes of supernovae may also contribute. Gravitational wave signals from neutron star mergers carry more than just mass and radius information. They also reveal the spins of the stars, the orientation of the system, and in some cases the equation of state at supranuclear densities. The post-merger oscillations, if detected, could provide direct information about the structure of the hypermassive neutron star remnant. Future observatories with greater sensitivity will be able to capture these high-frequency signals, offering new probes of dense matter. Mergers of neutron stars with black holes are another class of events now being detected. These systems produce gravitational waves as well, and in some cases tidal disruption of the neutron star leads to ejected matter and potential kilonova emission. The detection of such events expands the range of compact object interactions accessible to observation. Each merger, whether between two neutron stars or between a neutron star and a black hole, provides unique data on gravity nuclear physics and astrophysical transients. The detection of GW170817 and its electromagnetic counterparts demonstrated the power of combining gravitational wave and electromagnetic observations. Gravitational waves provide precise measurements of masses and radii, while light reveals the composition and dynamics of the ejector. Together they paint a complete picture of the merger. This multi-messenger approach has become a cornerstone of modern astrophysics, promising to answer questions about the origin of elements, the behavior of matter at extreme densities, and the limits of general relativity. Neutron star mergers thus represent both an end and a beginning. They mark the violent conclusion of long spirals that can last billions of years, but they also seed the universe with new heavy elements and generate signals detectable across the spectrum. Each chirp in gravitational waves and each glow of a kilonova carries the story of dense stars colliding and reshaping their surroundings. By studying these events, astronomers link the physics of the smallest scales within nuclei to the largest scales of cosmic evolution. The population of neutron stars observed across the galaxy reveals the diversity of these objects and provides the data needed to constrain their physical properties. Thousands of pulsars have been catalogued since their discovery, and surveys continue to find more each year. Most of these are detected in the radio band, where their pulses stand out clearly against the background of cosmic noise. Large radio arrays such as the Parkes Observatory in Australia, the Greenbank Telescope in the United States and the FAST Telescope in China have each contributed significantly to expanding the known sample. These observations allow astronomers to study pulsar distribution ages and magnetic field strengths. The distribution of neutron stars is not uniform. They are born in supernovae, and therefore they are concentrated in the disk of the Milky Way where massive stars form. Many are found in the spiral arms of the galaxy, often near star-forming regions. However, some neutron stars have been kicked to high velocities during their formation. Asymmetric supernova explosions impart recoil motions, so-called natal kicks, that can send neutron stars hurtling through space at hundreds of kilometers per second. These high-velocity neutron stars travel far from their birthplaces, creating a widely dispersed population across the galaxy. Proper motion studies confirm that many pulsars move at extraordinary speeds, some even fast enough to escape the Milky Way entirely. The measurement of neutron star masses and radii relies heavily on binary systems. In radio timing observations, the orbits of binary pulsars can be modelled with great precision. These models reveal not only orbital periods and eccentricities, but also the masses of the components. Some neutron stars in binaries with white dwarfs provide particularly precise measurements, because the Shapiro delay can be observed as pulses pass near the companion. These measurements have established that neutron stars can reach masses above 2 times that of the Sun, setting strong constraints on the equation of state of dense matter. Space-based X-ray telescopes such as NICER, mounted on the International Space Station, provide complementary measurements of radii. By observing hotspots on rotating neutron stars and modelling how their light curves are distorted by gravitational light bending, NICER has placed limits on radii in the range of about 12 to 14 kilometers. Combining these measurements with radio mass determinations yields one of the clearest pictures yet of neutron star structure. Each new observation narrows the possibilities for the behavior of matter at nuclear densities, guiding theoretical models. Population studies also reveal the evolutionary pathways of neutron stars. Young pulsars are found with short rotation periods and strong magnetic fields. As they age, they spin down and their fields weaken. Some are spun up again through accretion, becoming millisecond pulsars. The population of millisecond pulsars is concentrated in globular clusters, where stellar interactions are common and binary systems form readily. The dense environments of globular clusters enhance the probability of recycling, which is why so many millisecond pulsars are found there. Observations of these clusters with radio telescopes have revealed entire collections of pulsars orbiting within single stellar systems, each with unique timing properties. Magnetars form another distinct subpopulation. Their numbers are smaller, but their bursts and flares make them highly noticeable despite their rarity. Surveys with X-ray and gamma-ray telescopes have identified about 30 confirmed magnetars in the Milky Way. Their ages are generally young, consistent with their fields decaying over tens of thousands of years. Population studies suggest that a small fraction of supernovae produce magnetars, but the exact conditions that lead to their formation are still uncertain. By comparing the locations of magnetars with supernova remnants, astronomers can connect them to their progenitors and estimate birth rates. In addition to radio and X-ray surveys, gravitational wave observatories contribute to population studies by detecting mergers. Each detection provides information about the rate of binary neutron star formation in the universe. When combined with stellar evolution models, these rates help determine how many neutron stars exist and how they are distributed across different galaxies. The first detections have already shown that mergers are not exceedingly rare, and future surveys will refine these rates further. Neutron stars also serve as probes of the interstellar medium. Their radio pulses travel through the galaxy and are delayed by free electrons along the way. This dispersion provides a measure of the column density of electrons between Earth and the pulsar. By mapping dispersion measures across the sky, astronomers can construct models of the distribution of ionized gas in the Milky Way. In this sense, neutron stars not only reveal their own properties, but also illuminate the structure of the galaxy itself. The precision of pulsar timing has applications beyond astrophysics. Pulsar timing arrays use collections of millisecond pulsars spread across the sky to form a galactic scale detector for gravitational waves from supermassive black hole binaries. The stability of these pulsars allows detection of subtle correlations in pulse arrival times caused by the stretching of space-time. Recent announcements from timing array collaborations indicate that a background of low-frequency gravitational waves may already be present in the data. This result links the population of neutron stars directly to studies of black hole mergers on cosmological scales. The variety of neutron stars discovered so far suggest that many more remain unseen. Some may be too faint or too far to detect, while others may not be oriented in a way that their beams sweep across Earth. Estimates suggest that the Milky Way could host hundreds of millions of neutron stars, of which only a small fraction are observable. As instruments improve, especially in sensitivity and timing resolution, the catalogue of known neutron stars will grow, providing an ever clearer picture of their population and distribution. By studying the population as a whole, astronomers move from individual case studies to a comprehensive understanding of neutron stars. The observed diversity of pulsars, magnetars, millisecond pulsars, and accreting systems reflects the many evolutionary paths that follow stellar death. Population studies connect the endpoints of massive stars with the present-day galactic landscape, showing how neutron stars are born, how they change, and how they eventually fade. Each new detection adds to this statistical picture, refining the constraints on dense matter and strong gravity. In this way, the population of neutron stars forms not just a catalogue of exotic objects, but a framework for testing fundamental physics and understanding galactic evolution. Despite the enormous progress made in studying neutron stars, many questions remain unanswered, and these open areas of research define the frontiers of astrophysics. One of the central unresolved problems is the equation of state of dense matter. The equation of state describes the relationship between pressure and density in matter, compressed beyond nuclear levels. Different theoretical models predict very different behaviors, from stiff equations that allow stars to reach large radii to soft equations that produce smaller, more compact stars. Observations of heavy neutron stars with masses greater than 2 times the Sun's mass rule out many of the softest models, but uncertainty remains about whether exotic particles such as hyperons or deconfined quarks appear in the core. Determining the exact equation of state requires combining information from pulsar timing, X-ray spectroscopy, and gravitational wave signals, but the current data still allow multiple possibilities. Another unresolved issue is the mechanism of pulsar emission. The Lighthouse model explains the general behavior, but the details of how particles are accelerated and how coherent radio emission is produced remain unclear. Competing theories place the emission regions either near the magnetic poles close to the surface or higher up in the magnetosphere along the last open field lines. Observations of pulse shapes and polarization provide constraints, yet no single model explains all pulsars across the spectrum. Gamma-ray pulsars detected by the Fermi telescope, for example, appear to require emission regions far from the surface, while radio pulsars may involve processes closer in. This ongoing uncertainty reflects the complexity of plasma physics in ultra-strong magnetic fields and relativistic conditions. The origin of magnetars is another area of active research. While it is clear that they are young neutron stars with extreme magnetic fields, the exact process by which such fields are generated is not fully known. Some models suggest that rapid rotation at birth amplifies seed fields through dynamo action, producing fields in excess of a quadrillion times Earth's field. Others propose that magnetars are born with inherently stronger fields in their progenitor stars preserved during collapse. Observations of magnetar birth rates compared with ordinary pulsars may eventually clarify this process, but current data leave the question open. glitches also remain partly mysterious. The general picture of vortex unpinning in the neutron superfluid is widely accepted, but the details of how vortices move, how many participate in a glitch, and how they interact with the crust are uncertain. Some glitches involve sudden jumps, while others show more complex patterns with gradual changes. In magnetars, glitches are often accompanied by bursts of radiation, suggesting a link between internal superfluid dynamics and external magnetic stresses. Future timing observations may resolve whether glitches always require superfluid unpinning, or whether crustal fractures can sometimes occur independently. The possible connection between magnetars and fast radio bursts is a relatively new question. Fast radio bursts are brief flashes of radio emission originating from distant galaxies. They last only milliseconds but release enormous energy. In 2020, a fast radio burst was detected from a magnetar within the Milky Way, strongly supporting the idea that at least some extragalactic fast radio bursts come from magnetars. However, the full diversity of fast radio bursts, including repeating sources with complex patterns, may involve additional mechanisms. Clarifying this connection is a major goal of current observational campaigns. The fate of neutron stars at the upper mass limit is also uncertain. The maximum mass supported by the equation of state is not precisely known. Stars above that limit collapse into black holes, but the transition between stable neutron stars, hypermassive neutron stars formed in mergers, and black holes remains an open area of study. Gravitational wave observations of mergers are beginning to provide data on these outcomes, but much remains to be learned about how long hypermassive remnants survive and whether they leave observable signals before collapse. Another unsolved problem concerns the magnetic field evolution over very long timescales. While field decay is observed in magnetars and older pulsars, appear weaker the detailed processes of field rearrangement, the role of superconductivity, and the influence of nuclear pasta on conductivity are not yet settled. Observations of very old neutron stars, sometimes referred to as dead pulsars, are difficult, because they no longer emit pulses, but they may be detectable through thermal emission or interactions in binary systems. Studying these faint objects could provide insight into the ultimate evolution of neutron star magnetism. The interiors of neutron stars may hold surprises that are not yet predicted. If quark matter exists in the core, it could lead to observable signatures such as particular cooling rates, unusual mass-radius relations, or distinct gravitational wave signals from mergers. Detecting these would open a new window on quantum chromodynamics under conditions that cannot be reached in laboratories. At present, evidence for quark matter is circumstantial, but continued improvements in observations may eventually provide decisive proof. Observationally, the greatest opportunities lie in multi-messenger astronomy. The combined study of gravitational waves, electromagnetic radiation, and neutrinos promises to resolve many uncertainties. Future gravitational wave detectors with greater sensitivity will capture more binary mergers and reveal post-merger oscillations that carry direct information about dense matter. New X-ray missions with improved resolution will measure surface emission and hot spots with unprecedented precision. Radio telescopes will continue to expand pulsar timing arrays, improving the search for low-frequency gravitational waves. Together, these instruments will gradually narrow the range of possibilities and move closer to a definitive understanding of neutron stars. In summary, neutron stars remain objects of both knowledge and mystery. They are already known to test general relativity, to host exotic states of matter, and to produce the heaviest elements in the universe. Yet their interiors, their emission mechanisms, and their ultimate fates are not fully understood. The unanswered questions are not gaps, but opportunities pointing to where new observations and new theories will meet. As each new detection adds data, the picture grows sharper and the strange matter locked inside these stars becomes more familiar. Neutron stars will continue to guide research at the intersection of nuclear physics, astrophysics, and gravitation, offering insights not just into stellar remnants, but into the fundamental workings of nature.